So there is a small section here about the technology itself, or about the technologies. It's not highly technical. Again, first of all, I couldn't teach it as highly technical. But there isn't much need for us to go into it in, engineering level detail. There are some kind of key features that I want to remind you about and draw your attention to in this one, and then we look at one that has to do with sort of design, the same kind of general sort of orientation toward remembering about how important design is. We would probably be remiss if we didn't talk at least about this much about how this stuff works at the bottom of it. And so it's a pretty quick and dirty kind of treatment. If you've listened to the file and looked down the page, you know that it's not. It isn't particle physics. It is a reminder that we're still in a binary system. That's important. Okay. Now, will we one of these days get out of a binary system? It may very well be. With quantum, we'll move out of binary. Right now, the way we're doing quantum, it's still got kind of a binary feel to it. And right now, the way we're doing small or nano chip technology, right now also still has a binary feel to it. The way we're doing molecular right now kind of has a binary feel to it. In other words, there's this on-off XO12 thing that hasn't exactly gone away. Although in molecular and quantum and nano, there's always a chance that we may go to 4 or something else, right? With quantum, you will probably go to a different set of registers that come up, and then you code that. But right now, everything is still kind of binary, so we're still talking about bits on or off. Okay? And that changes the analog world, best as we can tell, because the analog world, best as we can tell, generally isn't in binary units in an on-off state. It's more sequential. It's more linear. Okay? Bits, as you know from the way everything that you do that's digital works, the signal can go both ways. If you think about electricity as sort of the archetype analog feature that isn't digital, right? You flip the switch and the current goes that way. And you hope it doesn't go back the other way, because if it does, you got a problem. Okay? You blow some fuses, you got a fire, you got outages, you got lots of trouble. The signals don't go that way. Okay? With digital, they go both ways, in the same piece if you want, right? In the same pipe, in the same, however you're shooting it. Okay? You select stuff and change those bits all the time. So you've got a picture open in Photoshop and you got a bunch of representations on the screen of bits. And if you go down close enough, you can actually see a pixel, right? As a little square, that representation of how everything is set with algorithms, and you can actually switch it. That's not a real good representation of the fundamental bit, but it gives you a sense of it. You can change its value by switching it, right? And those are strings, as you know, if you program, right? Strings of X's and O's that end up to equal some function, and then you put them in an algorithm, and there you go. A bit is a bit is a bit. It doesn't care what it is. So the same X and O string equals on the other side. Doesn't matter what it is. That string cares not. So you could make it equal graphic. You could make it equal sound. You could make it equal text. You could make it equal whatever you want, right? It's this mathematical thing that isn't like, how do I change this to leather? Oh, wait, I can't. Now, I suppose, someday if we get good enough with DNA and microbiology and all the rest, we might have a formula for changing whatever this is by changing its, structure. But that's a little far-fetched. Whereas right now, if I had a picture of it, I could change it to anything I wanted to. Right? If I have a virtual avatar, I can skin it with anything I want to, just by changing the bits. Moore's Law. Yeah. Moore's Law says this, roughly, every 18 months to 2 years. It's been pretty consistent. There are articles that will tell you that he has said we're going to hit a wall. There are articles that say we won't hit a wall. There are articles that say it's going to speed up, it's going to slow down. But roughly speaking, it's held up pretty well since he first proposed it. It was just a hypothesis about how it would work. And there are issues, and the issues that we've come to, there's a bunch of them, but for one, as speed and power have doubled, right? Cost has not come down quite as precipitously as we thought it might. It does in spots, and then it kind of doesn't. But it has sort of. You can buy an awful powerful computer for $800. You can buy a pretty good one for $500, right? So in some ways, costs have come down. There are some issues with this speed thing. We've gotten almost to the point where it's as small as it can get. What we etch on a chip in silicon is about as small as it can get until we go to a nanotechnology, which is a different kind of technology altogether. Then we don't know where that small limit is. But right now, etching on a silicon chip, we've got about as small as we can get and about as hot as we can get it. In other words, maybe on a silicon chip we're getting to the point where Moore's Law won't be much of a factor anymore. That is, it'll just stop us. Or, in order to increase it, which is the same thing as stopping us, it'll get so expensive that you just can't do it anymore. So while we might not see the end of it in terms of being able to etch the chip smaller, cramming all that business on a smaller chip produces heat. And keeping that chip cool is not easy. The more business you get on it, the hotter it gets when it runs. So we're kind of getting to where a lot of the engineers are saying, unless we come up with a different approach to this, we're probably not going to see these increases. But then they say, well, so here's a different approach. So we have different approaches, which I'll show you a couple, and you'll look at a couple. And if you go molecular, if you go quantum, you go nano, maybe the rules that apply to Moore's Law go out the window. Because the rules for Moore's Law were about silicon and that part of the industry. Okay? And for that part of the industry, it's been a pretty good predictor. But for some other way of doing computing that perhaps isn't binary and certainly doesn't use silicon chips, things might change altogether. Okay?